Hello, welcome to the recording or the substitute recording of review 2 for exam 2. Today I forgot to bring my power supply or charger for my computer. So I'm going to be more brief than the previous recording. I don't know whether you like it or not. I think some of you found my previous video was too long. So, first about the equation. This is a popular question from students. Uh, so I added two equations. I may add equation of the angular speed in mass spectrometry in a circular motion. So there could be another equation that I add, but basically my promise is always if uh, you will have access to all equations that you need to get a perfect score. And if if the equation is not there, then probably there will be one-step derivation that you can do. And then if you don't find that equation, that means the essence or the spirit of the equation is that I want to see whether you can do that one-step derivation, okay? Uh, and I know you can do it. Next is right hand rule. So the figure on the exam is not exam on the lecture notes and also on the exam. What I mean by on the exam is this figure here is two-dimensional, right? But this is not right hand rule. This is not right hand rule. Right hand rule, your thumb has to be 90 degree from the pointing finger and your middle finger is 90 degree with respect to the pointing finger and your thumb. Okay. And thumb represent the force. Pointing finger or middle finger is the direction of the magnetic field. And the pointing finger is the direction of the velocity vector or the direction of the current. Okay. All right. Next, so I've shown you that I will add this formula on the exam, and Lorentz force is also part of the exam. Uh, During lecture today, we discuss about velocity filter, and you can either watch the other video or ask me questions about it if it's still not clear. And then after velocity vector, we know the magnitude of the velocity. Because we know the magnitude of the velocity, then we can determine mass per charge. Okay, and and I think we didn't do this derivation in the review session, but this one is basically one-step derivation. Let me do it really quickly for you. Sorry, I promise that this video will be fast. But this one is basically mv squared divided by r is equal to q times v times b. So one of the v cancels. So r is equal to mv divided by b times q. Okay. So this is what I meant by one-step derivation, and r is equal to the expression of r in the equation box. Okay. Next is this derivation here. This one requires more than one step. So if there is a problem that needs this equation or formula, then I will put this formula in the equation sheet. Next, after the class, one of your friends, I think two of them, asked me about this problem. So basically, a battery, all batteries, they have internal resistance. Okay. One thing that I haven't mentioned in the class is that the internal resistance, a small r, increases over time. Okay. So at t equal to 0, we can assume that small r is equal to 0. But over time, it increases this because of that, then the potential drop is less than 1.5. Okay. So I think some of you discussed this question with Ross. Ross said the answer is B. I accept B as the answer because at is equal to 0, small r is not exactly 0. But in this class we do a lot of approximation. Because of that, at is equal to 0, I say r is 0, and if small r is 0, then the answer is C. But in this problem, B and C are correct. And then next, we I think we started with a discussion of solenoid. Basically, if there is a problem of solenoid, I try to draw it better. So here, instead of drawing it like what Pearson does, let me just make it bigger. I prefer drawing it like this. Okay. And then you can, of course, it can continue or it can stop, right? So oh, sorry. Made a mistake. Should be, yep, should be like this, okay? And the current either can go from this or can go from the other cable. That means it will have the opposite direction, okay? I hope it is clear. And then we did a long discussion about DC motor, but let me try to make it simple for you. So first, along every segment, there is non-zero magnetic force in the presence of magnetic field, and as long as the loop has circulating current, okay? But for example, in this drawing, this force here is identical. The magnitude of these two forces are the same. The directions are the opposite, so they cancel. Similarly, the force along the top and bottom segments, the magnitude is the same, but the directions are the opposite, so they also cancel, okay? Uh, and then the reason why, and then it makes sense, because for rotary machine, there is no linear motion, okay? There is no translational motion. Everything is rotary. Because there is no translational motion, then F is equal to 0. As long as there is F, as long as there is non-zero F, then there is translational motion. But this is rotary motion. So the torque for a different orientation can be either 0 or non-zero, right? Not always 0. Okay. So in the class, I try to simplify by, and your book try to simplify by using this symbol capital M. In chemistry, sometimes you use mu instead of capital M. And then the torque just M times B times sine of this angle here. So this angle is the angle between the normal vector and the magnetic field. Basically, briefly, if this is the angle of the normal vector, which is the angle of the M, okay, and it follows right-hand rule. So, okay. Basically, the so if in the presence of, let me change color, in the presence of magnetic field, a magnetic dipole or a magnetic dipole moment would like to align with the magnetic field. So at this point, the torque is 0. Okay. So this one here, see, let me just copy and paste here. Doesn't work. What's going on? Copy. Doesn't work. Anyway, let me just draw it. So basically, all right. So these drawings are basically identical, meaning the plane of the loop is perpendicular with respect to magnetic field. Okay. So here, because the because it's the position with the lowest delta G, or the most stable position, then the torque is 0. And we know for rotary motion, rotary motors, the force, the linear force is 0. So no net force and no net torque. Okay, so the answer here is D. Okay. Uh, in contrast, if this is magnetic field and the magnetic moment is perpendicular, this is when the torque is not only non-zero but is maximum. Okay, so as long as you know this, then you'll be good. Right. So B. So here B, which is there is net force, but there is no, sorry, there is a net torque, but there is no force. Okay. And I think at the end of the lecture, uh, there is a problem that sounds similar to this problem. So basically, suppose a resistor and a capacitor are connected in series to a battery. So there is a battery here. Does the value of resistor affect how much charge of the capacitor stores? All of you got it right. The answer is no. If no, what is the effect of the resistor? The effect of the resistor is that it will change the time constant. To be exact, time constant is R times C. And this is the time or characteristic time that required to charge a capacitor or to discharge a capacitor. Okay. So if you have any question, you should email me, and I wish you the best on your exam too. All right. Good luck.